Hello everyone, today we are going to explain about Laplace, Fourier, and also Z transform. Okay, but first of all, before we are going to dive into further explanation, we will talk about the brief history of Fourier transform, Laplace transform, and also Z transform. First of all, we're going to start with Fourier transform. Fourier transform was discovered by Jean-Baptiste Joseph Fourier, who was born on March 21st, 1768 in France. Fourier claims that any function of a variable, whether it is continuous or discontinuous, can be expanded in terms of adding the sign of the multiple of the variable. Next is about signal representation. A periodic signal can be represented as the sum of sinusoidal waves. Then sinusoidal waves have a fundamental frequency, and all waves are the product of that fundamental frequency. Here are some applications of the Fourier series in our everyday lives. It can be used to measure air waves, tune vibrations, sound waves, AC electric current, and in the medical field, it can be used to measure MRI signals and MRI scan photos. Next is Laplace transform. Laplace transform was discovered by Pierre Simon Laplace, who was born in 1749, who was a French mathematician and theoretical astronomer. Thanks to the expertise, he has made himself called the Newton of France. In 1782, Laplace began to study these integrals as solutions to differential equations, and according to historians, in 1785 he decided to reformulate the problem and gave birth to the Laplace transform. It is said that the Laplace transform exists if the previous integrals meet. Otherwise, it is said that the Laplace transform does not exist. In general, to indicate the function you want to change, lowercase is used and uppercase corresponds to the transformation. This way, we will have the current formula. Applications of Laplace transform is put into different engineering fields like electronics, mechanical, physics, etc. Besides this, Laplace transform is a very effective tool to simplify very complex problems in the area of stability and control. It goes without saying that Laplace transform is put to tremendous use in engineering field. And lastly is Z transform. This approach is quite complicated, and in a separate attempt to simplify matters, a transform of sampled signal or sequence was defined by in 1947 by Witold Hurwitz, as which was later denoted in 1952 as a Z transform by a sample data control group at Columbia University. The definition of Z transform is a transformation that converts discrete time into signals into complex forms in the frequency domain useful for solving differential equations. This is similar to the use of Laplace transform but applies to signals and discrete time systems. The Z transform is an infinite series, so it may diverge for some Z values. The transform is also defined uh, for an area where the result of the transformation is finite, named region of convergence. The region of convergence, or we call it ROC, of the minus Z transformation takes the form of R1 is smaller than Z and Z is smaller than R2, where Z is equal to lowercase r, with R1 and R2 boundary being dependent on the signal being transformed. Here are some everyday life applications of Z transform. First is obtain impulse response estimation, analysis of discrete signal, voice transmission, and it also helps in system design analysis and also checks the system stability. And lastly, is that it is also used in designing digital filters.
Now we're gonna talk about the formula. So here are the formulas as shown. So the difference between Fourier, Laplace, and Z transform. First, Fourier, used as a tool for the analysis of continuous time periodic and aperiodic signals. It cannot be used to analyze signals and systems that are not stable. Frequency response of a system can be drawn. Second, Laplace, used as a tool for the analysis of continuous time signals wherever Fourier transform is not applicable. It can be used to do analyze signals and systems that are not stable. Frequency response of a system cannot be drawn. And last, Z transform, used as a tool for the analysis of discrete time signals. It can be used to analyze signals and systems which are not stable. Frequency response of a system cannot be drawn. So this is the fun facts. The Z transform is the discrete time counterpart of the Laplace transform. In fact, it can be shown to be the Laplace transform of the discretized version of a continuous time signal. In the process, we obtain the S-plane mapping required by Z equals to e to the power of st. The Z transform converts a difference equation into an algebraic equation and hence is useful in solving difference equation. Z transform, like the Laplace transform, is an indispensable mathematical tool for the design analysis and monitoring of systems. The Z transform is the discrete time counterpart of the Laplace transform and a generalization of the Fourier transform of a sampled signal. Like Laplace transform, the Z transform of a sample insight into the transient behavior, the steady state behavior, and the stability of discrete time systems. A working knowledge of the Z transform is essential to the study of digital filters and systems. Thank you.